Welcome back, chat. Today, we are continuing on from yesterday. Remember, we talked about a bunch of stuff yesterday. Lowest energy that something has, we say it's in what state of matter?
A solid.
It's a solid. You start adding energy to it, and eventually you no longer have a solid, but instead you have a liquid. You keep adding energy to this liquid, all of a sudden, eventually you run out of liquid, and now you only have gas. And that's where we stop for that conversation. Now, we know that we can go a step further. Like, plasma does exist. It's most of the universe. Just real quick, with just memory, I want you, don't look at your notes. You can do this on the margin, or you can just talk about it. Do not write it down. You don't have to write this down. For this one, here's what I want you to do. I want you to tell me, if I have three states of matter, just right off the bat, S, L, and G. What do you think these represent?
Solid, liquid, gas.
Everybody okay with solid, liquid, gas? Okay, we're going to see this again. Here's what I want to know. If we have all three of these, I want you to give me the name of this, the name of this, and the name of this one. Without checking your notes, can you give me A, B, and C? Changing states from one to the other. Talk it out.
Liquid to gas.
I didn't know. Oh, that arrow fell off. C is liquid to gas. That's my bad. Max, great point. I don't know why it didn't show. There's an arrow here. Did you see Mr. Holloway? Did you see Mr. Holloway? Okay, maybe not.
Wait, what? Did I see?
No, I thought you said my name.
Oh, I thought
All
you
right,
said that.
who is feeling confident?
No, not very.
All right, Liam's feeling. Who doesn't feel at all confident? All right, Relly, you get a pick. What's your first one? What do we call it when something goes from liquid to a gas?
Wait, repeat that, please.
What do we call it when we go from liquid to gas?
Gas evaporation.
I'm okay with evaporation. Your main word is there. Somebody help. We take the E off. We just call it what? Max. Vaporize. Cool. Or maybe less cool depending on the situation, but that's all right. Now, looking at it, what if I want to go from a solid to a gas?
I forgot what it was called.
Importation.
Lovin' is what I got. Remember that, Jonah. This is called what? Sublime. To sublimate. That's a line from a Sublime song, if you didn't know that. Okay. What about the last one? Gas to liquid? Oh my, condensation. Awesome. Now, yesterday we looked at these ideas. We talked about the delta heat of vaporization, and we worded it differently. What do we call it? Heat of fusion and heat of blah, blah, blah. What's the other one we talked about? Heat of fusion and what? Heat of vaporization was the other one. Okay. So the data that we did yesterday, again, I want to stress you guys killed it in the lab. Didn't have to get on anybody about doing anything like really bad, so I appreciate that. Will somebody hit the lights? And then Relly had a question. Max, will you turn off the lights? And Relly, go ahead.
Do we get to go to the lab again today?
So we're not going to today. We will spend more time in the lab. I guarantee it moving forward. What I've done is, this is that vernier probe that I talked about. I went through and at the start of lunch, I had water cold already. And I just stuck a probe in there and told it to take a measurement every 30 seconds. And I let it run for like 40 minutes. Now, as I look at this, I need your guys' honest opinion on this here in just a minute. But what I see is, initially, what was the temperature of the water that I was about to start boiling? 5.3 what? 5.3 degrees Celsius. Now, it slowly increases to begin with, right? I jump by 0.2, and then from here to here, it's another 0.2. And then look at that, we start kicking. And all of a sudden, we start heating up more. Now, as I go, I keep heating up. And there's a bunch of measurements here. After 6 minutes, I was already at 20 degrees, 22, which is like lukewarm. Another 5 minutes, or after 10 minutes, we're at 43, which is getting to be uncomfortably hot. And then anything beyond that is going to be like possible burn. Yes, sir.
Why was there one measurement?
I think it's just the one that I'm clicked on, just so it says I highlighted it. Okay, now, here's the question that we didn't get to yesterday. Most groups got somewhere in here. Somewhere in that range. Some of you got to 90. I can scroll down further. How hot will my water get? So it can get to 100. Some people say over 100. Now, there's a weird thing that happens here. If I were to look at this, here I go, I'm still heating up, and then check it out. For this, the last 10 minutes, I had a rolling boil where everything was still 99 degrees. I kept adding energy to the water for these last 10 minutes. Like, it was cranked up to like 450 degrees over there. It was super hot. Here's the weird thing, though, or maybe it's not. Why doesn't my water keep increasing in temperature?
When it evaporates after.
But I'm still adding all that energy. Do you think the steam was hotter than this? Energy can leave by the steam. Love that idea. We are radiating some energy away. Now, here's a question that I need complete honesty for. You guys came from math and maybe got kind of pwned this morning. Last hour. I don't know when it was. I don't think people say the word pwn anymore. Fun fact, pwn was a really common phrase in like the mid-2000s because somebody had a typo. Instead of an O, because they said, I owned you on a video game, they pwned them. And it just stuck. Dumbest thing ever. Okay. With that in mind, can you guys graph points? Can you do so well?
No.
Okay. It does not have to be super duper specific. I'm going to make you guys graph like 8 points for me real quick. Now, I don't care if every person does this completely individually or if you divvy up the labor between the two of you. As long as you're talking about it, I'm fine with it. There is graph paper coming around. If you want to do your own and you want your neighbor, excuse me, to also do one, I'll just say rip this in half. I have more graph paper if needed as well. We're going to pick 10 points for you guys to graph. I don't know that I marked rightly absent now that I'm here doing this, so I better check that. Did a couple pieces. You got a piece. Cool. Let's pick our points real quick to do this with. Now, we're going to graph. And I need you to graph. I need to check to see that you can graph it. We're going to try to draw it to scale. But let's get some points. You do not have to measure exactly with decimals, just so you're aware, okay? All right. So we're going to get 10 points. We have time in minutes, or, yeah, we'll do minutes. And then we have temperature, and we recorded it how? Degrees Celsius. Awesome. Now, you guys, I have your stuff from yesterday. I'm going to give you grades for doing it. Like, I appreciate you guys working in there when we were in there. My data is the same as your data. I just have it all. So we're going to pick a few random spots here. Let's say that at, 12 minutes, I was at 54 degrees. 12 minutes, I was at 54 degrees Celsius. All right, and then what's another time you want? Let's do 15. At 15 minutes, all of a sudden my water was at 70.5 degrees Celsius. I'm not going to really make you do 10 points. That seems like too much. Okay. Twist my arm. Do you guys know that saying? Like, is that a common one? Twist my arm? Do you know what it means if I say that?
Like twist what you said. Like,
No, like that'd be twist my words or misconstrue it. You ever watch a cop arrest somebody?
yes.
So they'll probably move their hand back here and then they pull it up because it hurts. So they're twisting their arm to like control them, right? So if there's something that I want to do and you guys are like on board with it, I say, well, twist my arm. Like I'm saying, yeah, you can make me do it, but you don't really have to because I also want to do it. Maybe that doesn't make sense. Maybe it makes dollars. All right, thank you. At 17 minutes, we're at 80.5. We decided 5 points, right? I think I'm probably going to lie and give you 6 or 7. 20 minutes, we're at 93. All right, 22 minutes, we're at 98.3. Then the last 3 points that I want you to do for me. At 24 minutes, we were at 99.2. At 27 minutes, we were at 99.2. At 29 minutes, where were we? 99.2. Sonny, I think it's awesome if your calculator can do it, and that speaks for a few of you guys. Don't care if your calculator can do it, though. I care if you can do it. Draw me a graph. I'm going to come around and be real judgy about all of your points. Sonny, do it on paper. Cool. I will give you guys a couple of minutes. If you have questions and you have no idea how to plot a point, could you ask somebody? Who?
Oh my
You could ask your friend. What if they look at it and they explain it and you go, I don't know what you're talking about.
Then the
Hey, this guy. Cool. Plot points make a scale. I'm going to be real judgy about it. I'll give you a moment. Here's our 7 or 8 points. If you struggle with this, here we go. Looking at it, is my graph going to be perfect? No, but is it going to be awful? No, I don't think so. Now you don't know what I mean by awful, so maybe it will be from your point of view. Do I need any negatives anywhere? So which quadrant should I work in? Quadrant 1, the very top right. When I look at this graph, not that, when I look at this graph, I start by doing this and saying, look, everything is positive. Here it is. Now, I don't have graph paper to do equal marks, but I bet I can eyeball fairly okay. I need, on this axis, what do we decide this was down here? Time or temp? The time is what determines the temperature. Cool. So the time in minutes is down here. And then on this side, I'm just going to say degrees Celsius. Now, when I'm graphing, and when you're graphing, we probably do things a little bit different. Quick show of hands, who in here, whenever you graph, you automatically jump to a 10 by 10? Like, it's the one that naturally shows up. You guys, everybody in here mostly adjust your scale?
No, I do that. I was
Most people, not everybody, most people probably start just by doing a big graph like this without looking ahead at all. If you don't need negatives, don't include negatives. Let's save some work. Okay, with that in mind, if you struggle with setting up a graph, my time ranges from, I didn't include it, but it was 0 to how far out? 0 minutes is my very first one. I didn't even put it here. And it goes all the way out to how far? 29 is what I have. Is counting in 29s easy? Is 29 close to something? 30. So when I'm looking at this, I don't have any graphs. If I make this tick, for example, 5, then this would be what? 10, 15, 20, 25, and 30. I don't have graph paper. That worked out much better than I was expecting it to, just full disclosure. I didn't think it was going to be perfect. It came out pretty good. Okay. Patted myself on the back if you guys didn't catch that. This is 30 minutes, right? All right. I'm not going to label the other ones because if I use the same jump, I don't have to tell you it's different. Like they're the exact same, every one of them. Temperature ranges from where to where? 54 to 99. Now I'm going to hook it up. I'm going to give us one more data point just so we can include the y-axis. If you already have your y-axis or your temperature axis, this vertical one, you guys probably don't remember. I know I don't. At time 0, my temperature was 5 degrees. So I'm going to say 0.5 was the last point, and it would really go here. I started with 5-degree water. Only reason I'm giving us that data point is so I can see the y-intercept, where my graph crosses it. And let's see. My temperatures then range from 5 up to what?
Oh, wait, 54.
5 to 54 is the first jump. And then it goes to 70, and then to 80, then to 93, and 98, and 99, and 99, and 99, and 99, and 99. I probably just need to go from 0, including 5, all the way up to what temperature? What's the hottest my water gets?
99.2.
Am I really going to put 99.2 on my graph? What should I put instead? I would rather do 100. 99 would be okay, but check it out. Because we're just sketching, and I don't know how hardcore Russell makes you graph, doesn't matter where I pick. If I say this is 100, it's 100, right? Which means if I eyeball this out, what's this? Which means what's this? And this here would be? Now, because we're just sketching, I think that this is okay. I'm not going to be perfect with my 0.3s and whatever, and I probably won't even be perfect with my 98, but I'm going to be able to roughly get these points. Do you guys agree with that? Right off the bat, is there any part of this process, or let me rephrase that, which part of this process have you seen and go, I don't know what the heck you just did, Holloway? Hit it.
We picked our not the how much we jump for graph.
Absolutely, you could jump differently than I did. 100%. Unless you're asking, how did I pick it? Okay, yes, you could jump by ones if you want. I'm never going to count out little ones. All right, now plotting points. If I wanted to plot this first point, 0 and 5, it was 5.5, but I'll call it 5. Here I'm at 0. You guys get real loud when you think I'm at 5.
That's too far up.
I just screamed.
That wasn't yelling. That wasn't real loud or crazy. Here? Would you believe it if I told you that was 5?
No.
Why?
Oh, yeah, I would.
Because this is 12.5. I know that. Which means that this would be 6. So maybe I'm a little bit high. But estimated, I'm okay with this. Okay, at 15 minutes. So here's 5 and 10 and 15. You shout when you think that I'm at 12 minutes. So here's 5 and 10, and then that's probably 12. And then I go up how high? 54. So here I am. You tell me to stop. I believe it. Probably about that, right? Okay. That was good. Okay. Next one. 15. I'm up to where? 70. So I'm just going to eyeball it. I think I believe it there. It's not perfect, but it's close. Okay. If I keep doing this, I have the sneaking suspicion that it's not going to be perfect, but those kind of look like they're in a line to me. I bet the next point will also fall on this line. Does that seem reasonable to you? The first 3 points were in a straight line. This next one probably will be. And it stays there up until 24 minutes, which, and I'm looking at it, I'm eyeballing it. Mine's not perfect. 24 minutes would be right here. So my line's a little bit off, right? That's okay. At 24 minutes, what was my temperature? So here's 24. It was 99, right? Do you agree it's there? Now, I didn't graph perfectly, but are those pretty close? Like, it looks like a line of fit to me. Now, the second I got here, I kept recording for several more minutes. What happened to the temperature value? It flatlined, meaning what? It doesn't rise, it doesn't fall, right? It just stays like this. Now, we are looking at one little portion of this. How long do you think the water that was in the beaker as it boiled, when would it stop being 99 degrees? So what if I don't turn it off? I liked your answer, Sunny. Can you say that louder? When there's no more water and all that I'm heating is steam, I'd be allowed to go past this mark. You will never get at standard pressure, which just means anywhere naturally on Earth, you'll never get water that boils hotter than this. Now, with this idea is only liquid to gas. What do you think we would see if we had a block of ice and I started adding energy to it to melt it? I would keep increasing in temperature until I got to what magic number? 0. Would I stay at 0 for a while? Or would it just automatically start increasing, do you think? Just like this stays at 0 until all the liquid is gone, the ice would stay at 0 until all the solid is gone. What we see here is a heating curve. Now, just so you guys can see, because these things are awesome, the math part of it is obviously important. Here's the graph that this thing made for our data. This is what the graph came out with the real information. Cool. We are going to summarize this. Vincent, your turn. Yep. Cool. All right. Looking at these, let's summarize what we've seen here. The graphing part, everybody feels okay with. Okay. Coolest person in the room right now is? Awesome. Uh-oh. All right, decision. Who's really cooler, me or your principal? Yes, I think you just follow Ms. Morris. Cool. All right. Baller. I didn't know if you guys were going to waver. I'm proud of you for committing. Sticking with me. I like it. Cool. All right. Should we take a quick brain break before we generalize this? We talked briefly earlier this year. Cool. Break your brain some more. Love it. Here we go. Checking this stuff out. We had a heating curve. We're going to look at the more general sense of this and see that, hey, these things show up all over the place. When we defined a heating curve yesterday, we said all it does is it shows how states of matter change with energy. Now, you can't add infinite energy super fast, so they have to happen with time. So whenever we're looking at these, in general, we get the following. And we're going to do an example. You guys should have this in your notes. Whether it's water or not doesn't matter. We'll say this is some unknown substance. Now, gallium would be a cool example, but let's check it out. If we have some unknown substance, I'm not going to put any numbers on this, but we are going to put a few letters around these spots. We have time that must move if we're going to keep adding energy to something, and we have its temperature in Celsius we'll use. Hypothetically, let's say that we started, I'm going to move that one down just a little bit more. Let's say I started down here, which means you don't give me an actual number because we don't have a scale whatsoever. But can you tell me anything about the temperature at that starting point? It's negative. It's below 0 right now. Cool. So let's say we start adding energy. And if it's this cold, it's probably a what? Not necessarily. It's probably a solid. Okay. So let's see. We start adding energy to it. Could I increase the temperature? Like, and this is a weird idea. Just not that isn't a weird idea. But if you have ice, like an ice cube, regular water, what's the temperature of it in your hand?
0.
You're probably natural to think 0 Celsius or 32 because it's a frozen piece of ice, right? Could you have colder ice?
Yeah.
Like if I have ice that formed in a cooler that was negative 50, could I have ice then that is negative 50 degrees? Could I heat that ice up so that it's now like negative 30? So I've heated up the ice, but it's still ice. We have colder ice and warmer ice. Just like you have colder water and warmer water, the same thing works with ice and temperature. Metal gets really hot before it melts, right? Same concept. Okay, now let's hypothetically say I added energy and I see the temperature stops here. We're going to call this part A. This whole piece. And then all of a sudden, as I'm measuring this and I still have it on the same hot plate, I haven't changed temperature, it does this. Just flat lines for a minute. We'll call this section B. Then, still more time ticking along, we add more energy, and we keep adding energy and adding energy and adding energy until we get here, and it flatlines again. We'll call this C and D, respectively. And we'll just stop there. I've not told you what this substance is. I don't even know. We're just talking about some random substance. Have I told you any temperatures other than negative and positive? No. What I want you guys to do for this heating curve is I want you to be able to identify and justify the following. I want to know, and we're going to add a couple more points. We're going to add E, F, and G here. Okay. I want to know at what point in all of these is the melting point. Where is melting point? That's my first question. And I'm going to pause this so that whoever's watching, if there's anybody watching, I still need to do attendance, I'm pretty sure. All right, if you're watching this at home, which I think everybody's here, so that's probably not happening. Ah, right, that's why. Yes. Yes. I didn't count, didn't even look. That's my bad. Cool. Talk these out. We'll come back together in a couple minutes. Talk. Loud, loud, loud. Yes. Too many unknowns. Would it help if we made some more knowns? Now, I'm not going to tell you what the substance is because I didn't pick a specific substance. Let's pick some temperatures. I'm fine with picking a scale for temperature. You tell me when to stop here. Can we agree that's 0? I don't have to write it? Okay. So let's pick some scales. Pick a temperature. Don't care what it is.
50.
Sure. Where else do you want to put a temperature? I guess if that's 50, that'd probably be 100, huh? And then roughly the same amount up would be 150? Okay, I'm good with that. Do you want time? I don't know that we really need temperature either, but we can add it. Whoever this is, anybody in here?
That's fine.
5.
Yeah.
That's fine.
5.
6890 is calling you. Don't know who that is. 6890.
Isn't that old?
All right. I have no idea. So check it out. Looking at this. Let's just see if we can't piece this together. We got half of this picture a minute ago when we drew our heating curve from the data with the water. Okay, when we have the coldest version of this substance, doesn't matter what it is, do you think it starts as a liquid, a solid, or a gas?
At what point? Wait, where?
It better be solid. The colder stuff the more it packs together, right? So, what I know is that in this section, state of matter, from when I start all the way to here, you guys just correctly identified, this should be a solid. At A, or along A, this is a solid. We'll come back and we'll hit the next part. Now, if you want to think about it like a block of ice, that's fine with me. We'll come back. I was solid all along to here, and then the temperature kind of mellowed out. What do you think I am here? So I was solid, and I kept adding energy. C, I think I'm a liquid. Now, if I had gone one further step, and I'm not, like, you don't have to add it, but what do you think I am here?
That's solid, yeah.
Probably a gas. Seems reasonable, right? Okay, so with that in mind, we've identified the states of matter. I have solid here, I have liquid here, and I have gas up here, if I get to it. Where do you think the vapor point, or more common language, the boiling point is? Where do you see me changing from a liquid to a gas?
Like in between C.
I don't know. All right, so checking it out. If it's the boiling point, are we changing liquid to gas or solid to liquid?
Solid to liquid.
If you put a piece of ice on the counter and it melts, do you say it boiled?
Milk.
It melts. That'd be my melting point. At which temperature did I start changing from a solid to a liquid? 50 on this, or at which point? E is where it starts to happen. Now, at E, I now have started to melt whatever it is. We'll pretend it's ice, whether it's water or not. Here to here, I keep adding energy, but the temperature doesn't change. Instead of the energy that we add change the temperature, it's changing its state. We're still adding energy, but it's no longer increasing the temperature. It's just changing the state of matter. Once we get to C, we're in a liquid. And it stays a liquid until it gets to some magic point where it starts to convert to gas. Where does this happen? Where we go from liquid and we get hot enough that all the extra energy. D is where we're at boiling. G is the actual point where we start to boil. Now, once I have boiling water at 100 degrees, for example, it stays 100 degrees until all the water's gone. That means that once I'm at the boiling point, all of this, what am I doing? I'm boiling. Cool. At D, we're just boiling. What are we doing here when I get to the temperature where I start to transition from a solid to a liquid? I'd call it melting. Okay. These graphs, for anything that we ever deal with, they will have essentially the same shape. This substance, no idea. Don't even know if it exists. I made it up. There are things that boil at 50 degrees, or sorry, that freeze at 50 degrees and then boil at 110. That does exist. As we go through here, follow-up question. I promise it's not a trick, but it might feel like it. I want you guys to address, just via discussion, I want to know what is its condensing point and its freezing point. I'll give you a second. From this graph, after everything that we just worked out, at which point does this condense and at which point does this freeze? I will give you a moment. Well, let's talk about water just real quick. At what point does water freeze? At 0. Okay, if I have frozen water, at what temperature would it start to maybe think about melting? 0. They're the same thing. If we've identified the melting point, what have we also identified for free? The freezing point. They're the same number, and we even have that in our notes yesterday. Once we find the boiling point, what else do we get for free? The condensing point, where it turns the other way. They're just opposite directions. Now, going through here, we have a lot of meaning in this. Okay, we're going to talk about a couple more things. I will write down if we need to, but I think we can talk about it just as a whole to begin with. Typically, what happens when stuff gets hot? If you guys were near each other and you were all warm, would you get closer together or spread out? What do particles do when we heat them up? They spread out. They get more energized. They start to space themselves out a bit more, right? Are you made of particles? Now, if you get heated enough, all your particles spread out so much that you're just not you anymore, and you would have been cremated at that point. Okay, we're not going that far. With that in mind, if I take metal and I heat it, and before it melts, what do you think happens with the metal? It does turn red hot. Do the particles try to spread out? They try to, but metal's kind of hard, yeah? So they can't actually just piece out. But they do expand. Stuff gets warmer as it heats. Have you guys ever seen that in your life? Sorry, everything gets warmer as it heats. That's the wrong statement. Stuff gets bigger when it heats. Okay, if you've never had to try to take off a bolt that's stuck on, you can heat it to make it bigger to get it off. Like, that's a common technique. Yes, sir? Okay. I don't know which one's yours, but I'll trust you. Cool. All right. I lied. We're going to have to write this down. We're going to go quick, though, or less writing. Thermal expansion. That was much more aggressive than I meant it to be. I'm sorry. Okay. Thermal, yeah, just going yak in here. Now, if stuff gets warm, it gets bigger. Like most things. Metal especially does this. Metals will swell. As we're looking at this, we're going to say thermal expansion is just simply the increase in size. The increase in size with an increase in temperature. Now, for this, most of the time this works. Higher temp means expanded. There's one particular thing where this doesn't quite work really well with. Now, as we go through this, we take advantage of this all the time. Yesterday in the lab, I made you guys submerge what in the boiling beakers? A thermometer. And that thermometer, what happened as it got warmer, the red line moved up, yeah? Why? It got warmer and it expanded, which is the same answer. They're just different words. Now, I don't know if you guys have seen this, and we'll see if I can find it here. Surely it's in here. I probably should not have mentioned it before I found it.
Is it in the lab?
I think it's in the lab. I'll go grab it here in a second. Okay, thermometers make use of this, 100%. Thermometers use the fact that things get larger or less dense as they heat up. Okay.
Do you know what it's called? The substance inside of the thermometer?
It used to be mercury. I don't know what they use today. It used to be liquid mercury. Okay, beyond that, anything else that you know this happens with? If you want to fly but you don't want to get in a plane, what are you going to do? You're going to fly in a boat?
Jetpack.
So you might get in a helicopter. That's even scarier.
Jetpack.
What about like 100 years ago, 200 years ago, before planes were a thing? How would you fly if you wanted to? So I guess you'll fly for a second. Maybe a wing. So gliders, they weren't invented yet. Da Vinci came up with one in like the 1500s, which is super cool. A hot air balloon. Okay, hot air balloons do exist. How do they work? When you heat air, air does what?
It makes the thing.
I thought it goes up.
It expands.
It expands. It expands, which means the same air is now further apart. It has lost density. Lower density stuff goes where?
Way up.
Up.
I thought it
Okay.
was heat travels up.
It does because it's lower density. Like that's exactly why it happens. Okay. Hot air balloons, thermometers, thermal expansion. They all take advantage of this. Now, on the other side of this, there's a weird situation. Most things do this. Water is not most things, just so you know. Water is exceptionally unique with the idea of thermal expansion. When water cools down, what happens? If I have a can of soda or a bottle of water, doesn't matter, and it's completely full, I haven't opened it yet, and I put it in the freezer and I forget about it, what am I possibly going to come back to? It got colder and it exploded, right? Why does that can of soda explode in the freezer? It expands, but what is stuff supposed to do when it gets colder?
It's smaller.
Do you see the issue with water? And it's not even so much of an issue, but it's something really unique about water. Water does not get smaller forever. Like it doesn't keep condensing like everything else does. When we look at water, it is unique. We're going to say that this condenses until about 4 degrees Celsius. So we can look at this, and if you ever take earth science, you'll see this idea talked about when we look at heating, and we already looked at it in here. It's called convection, remember, when we have that movement. Cold water sinks because hot water rises, and it fills a spot. Now, water does this in a weird way. It does condense until 4 degrees. But after 4 degrees, it starts doing this crazy thing that nothing else on our planet does. Below 4 degrees, instead of keep getting smaller because it's getting colder, what does water do? It starts to expand. After this, ice or cold water, below 4 degree water, it expands.
Is water the only exception?
Water is the exception that I have off the top of my head. I can't think of another thing that does this. And we are so fortunate that it does. Because if it didn't, what would happen to all the fish and life in the lakes when they freeze? Like the ice would form, then it'd sink and crush them all to death, and we would say goodbye fish. Now, this is super duper unique. The way this happens, and we're not in a hardcore chemistry class, but you wind up getting atoms that align themselves instead of just getting really close together, they do so in a special way that it forms crystals. Just like crystals in a diamond, ice works the same way. Okay, last little thing. Are you okay if I don't write any more than that? Yeah. All right. Whew. Let's check a couple things real quick. Where does water melt? 0 degrees. Cool. I kicked it way too hard last time. Where does lead melt?
Lead?
Why would you know that, right? Anybody have a guess?
17.
Lead is super solid. It's a metal.
85.
That's a good guess. It is 327 exactly. Okay, so that was all right, whatever. It's just a guess, right? Like, that's fine. Do we agree that lead melts at a specific temperature, though? Like, all metals will, right? If I have a metal and I heat it up, there's a point where it starts to become liquid. Okay, those are easy questions. What about butter?
Butter?
When does butter melt? And do you think we would agree?
Room temperature.
At room temperature. Anybody at home leave butter out? Yeah. I do. Does it melt all over your counter? No. So it must not be room temperature. Now, there's something different about a block of ice. We can all agree when it's melted because it looks like water. Metal, we could agree as well. It was metal, now it looks like liquid metal. It read like it's hot, whatever. Would we all agree at the exact point when butter is truly melted, do you think? Like, there's a point where it's all completely liquid, but there's a middle ground with butter. Something different about it. It's not as well defined. Do you guys agree with that? Yes. There's soft butter, and there's softer butter, and then eventually there's liquid butter, and there's a whole lot of middle ground. With that, we have what is known as a without specific change solid, and it has a better word, amorphous. A, just for like, I'm trying to think of a word where it's a negation. I'm going to write it just so you can see it. Amorphous. Not a single morphous, but an amorphous solid. Easy to define. Butter's an example of this. Jello's another one. What is Jello? So it's gelatin. Is it solid? Is it?
Wait, it's like solid.
It's in the middle ground, right?
It's kind of in the middle ground as well, right? Like, I would say it's more solid than liquid, but if you start heating it, it starts to get more runny, but it's not quite pure liquid. It's another amorphous solid. As we look at these, we're just going to say no defined melting point.
It's just like the stuff that, like, if you hit it hard. The stuff like if you,
Oobleck?
yeah, Oobleck.
Those are non-Newtonian fluids. Similar idea for sure. Okay. Cool. Last little tiny piece of this. And we're going to have just enough time for you to give you an assignment. You use these all the time. Amorphous solids exist, and I bet they're in your house. You're probably looking at some amorphous solids right now.
Air.
What's behind this screen here? So I don't think this is LED. That's a good thought. There are wires. This isn't LED. This is probably a LCD. What's LCD stand for?
Liquid.
Ooh. It's a liquid crystal display. Okay. Within this, there are amorphous crystals that aren't fully solid. They're not liquid yet. They're somewhere in between. By pumping different amounts of energy into each of those crystals, its density changes just enough to change the color that we see on the screen. You use this probably every time you look at your phone if your phone's older than 2 years. Okay, over the weekend, I got you, don't worry. Homework. I do. 14.1, it's not bad. Page 361, and you guys get problems 1 through 7. I didn't want you to have to wait until Monday at lunch to think of my class again, so I got you. I mean, you should, because now you have homework to think about. Remember me with this, Sonny. Somebody was singing Wicked in the hallway, and I just want to let you know that it's stuck in my head now, and I'm very upset. All right, those of you traveling or out here are our questions. All right, later, guys. If you choose not to take your book home, the last 20 or so seconds of the video are the assignment. Cool. Later, Raiders. No, I stopped about I only needed like 5 minutes.
Oh, I've been looking at it.
Oh, yep, I stopped it.